This video is just about the operations on functions. That's kind of an intimidating sounding title, but it's a pretty straightforward idea. Let's just jump right in. So what does that mean? Well, one of them is like addition and subtraction. Like those are two different operations on functions. And what it means is like, all right, we have two different functions, add them together. This is what we've called in like Algebra 1, we call this like simplifying or combining like terms, but that's really all we're doing here when it comes to addition or subtraction of functions. So for this one, right, it's saying f of x plus g of x. So we say, 6x squared plus 5, that's f of x, right? Plus, because of plus, and then g of x, x squared plus 3x minus 4. And we just combine like terms. So we've got an x squared and a 6x squared, 7x squared. We've got a 3x, so plus 3x, and we've got a 5 and a negative 4, so plus 1. And that's it. That is f of x plus g of x. Now f of x minus g of x is the same thing, except for we have the minus, which means we need to be conscious of distribution. If students mess up on a problem like this, it's because they forget to distribute a negative. So don't be like that. So 6x squared plus 5, that's f of x, minus, to help you with this, I just would recommend that you put g of x, if it's a subtraction, always put it in a parenthesis so it's like clear that you need to distribute the negative. X squared plus 3x minus 4. Distribute the negative through now, we get 6x squared plus 5, that's a 5, minus x squared minus 3x and plus 4. The negative distributes to everything, so combine like terms now. We have 5x squared, we have negative 3x, and we have a 5 plus a 4 plus 9. That would be f of x minus g of x. Okay, now we have g of x, and f of x again. They're a little bit different, and I want to now multiply and divide. So this is a little bit more complicated in that we're going to need to employ things like distribution, and we're going to need to kind of be conscious of factoring and canceling and stuff when we're dividing. But the other thing to consider here is that we also need to be conscious of the domains. Because, I mean, if we look at g of x and f of x as they are, both of those have domains of all real numbers. The g of x is a parabola, it's a quadratic, so it's a parabola, the domain is all real numbers, and negative infinity to infinity. And then f of x is just a line, right? It's a line, the slope is not undefined, therefore the domain is all real numbers. And we have no restrictions for either of these. But when we combine them by multiplication or division, it's possible that we will. So let's see. F of x times g of x is going to be negative 3x plus 5. That's what f of x is, right? Times g of x is x squared minus 2x minus a. So this is a little tedious in that we're going to have to do some big boy distribution here, right? And distribute all three of these terms. So it'll be negative 3x times x squared, which is negative 3x cubed, negative 3x times negative 2x, positive 6x squared, negative 3x times negative 8 is positive 24x. Okay, then we have to distribute the 5 into all three of the terms over here, right? So 5 times x squared, positive 5x squared, 5 times negative 2x, negative 10x, and 5 times negative 8 is negative 40, and then we just need to combine like terms. So we have negative 3x squared, 6x squared plus 5x squared is positive 11x squared, 24x minus 10x is positive 14x, and then minus 40. So that's what we're working with for f of x times g of x, which would be the same thing, by the way, as g of x times f of x, because multiplication is commutative. Right, now f of x divided by g of x. Okay, so notice, right, we're going to have a denominator here. So if we just literally write what this says, it's negative 3x plus 5 divided by x squared minus 2x minus 8, right? This is g of x and this is f of x. We have a problem here because, well, first of all, we have to check, does anything cancel, or are there any like factorizations we need to do? The domain of this one, let's just back up, is negative infinity to infinity. There's no factoring we can do here. Yes, we can factor the denominator, and we're going to in a second, but it wouldn't like cancel out anything with the numerator. So let's just simplify. Negative 3x plus 5 divided by this denominator factors to x minus 4 times x plus 2. So there is f of x divided by g of x. However, we have a domain restriction here now, right? We have a divide by 0 problem. So we need to figure out what values of x would make the denominator 0, and those two values are that x cannot equal +4 or -2. So confer with your teacher about what way they'd like you to describe this domain, but sometimes it's okay to just say this is f of x divided by g of x, but x cannot equal 4 or -2, or you can write the domain. You can write something like the set of all x such that x cannot equal -2 or 4, or an interval notation, which is a little tedious, but no big deal. -infinity to -2 can't be -2, -2 to 4 can't be 4, and 4 to infinity. So we just got to keep the domain in mind. When we have a denominator, we got to make sure we can't have a denominator of 0. When we have a radical, we can't have a negative under there. Remember, those are the two things. So we would have an even radical, so a square root, a fourth root, a sixth root. Those are the two things that cause restrictions to the domain. Okay, now the bigger idea here in this little lesson is composite functions, just composition of functions, different ways to describe the same thing. And in the how this is represented to you in your class or in your textbook or by your teacher might differ, but you'll see like 3 different ways primarily of describing what this is. You'll see this thing that looks like fog, F-O-G. You'll see this f of g, and you'll see f of g of x. This is called f of g of x. All 3 of these things are describing the same thing. It's asking you to plug g of x in for where you see x in f of x. And then same thing here, just opposite g of f of x, g of f, g of f of x, g of f, g of f, g of f of x. Okay, so let's do this for an example. Here we go. If g of x is x squared plus 5 and f of x is x minus 3, what is f of g of x? And then we're also going to talk about the domain. So let's do this one first. F of g of x. What that's saying is take f of and then plug in x squared plus 5, right? So we're going to take f, which is x minus 3, but here we're going to plug in the x squared minus 5. So this is x squared minus 5 minus 3. So f of g of x is going to be x squared minus 8. That's it. Now there's no domain restrictions here. This one we don't have to be super worried about domain, because the domain of our original terms here is it's all real numbers here. We don't have domain restrictions for our original functions. We're not going to end up with domain restrictions for our composite functions either. Okay, that's going to come into play soon. We're going to do more examples. All right, now g of f of x, again, that's just saying g of, then we're going to plug in f of x, which is x minus 3. All right, so remember that g of f of x, or remember that f of x is x minus 3, right? And g of x is x squared minus 5. So what this looks like is we're going to plug in, squared, right? It's the x is being squared, and x is now x minus 3, so it's x minus 3, right? That's all this is. So when we FOIL out x minus 3 quantity squared, it's x squared minus 6x plus 9, and then there's this plus 5 at the end still. So this becomes x squared minus 6x plus 14. Again, this is a parabola, so we don't have, there's not going to be a domain restriction here. There wasn't a domain restriction originally. That's what it's like to plug a function in. So both domains is negative infinity to infinity, or for all real numbers, however your teacher wants you to say that. All right, now we can also do evaluate these. So you can do this a couple different ways. You could say, for example, right, we said that f of g of x, we already know what it is. It is x squared, it was x, well, gosh, what was it? It was f of g of x. X squared, did I do that last problem wrong? I don't remember what it was. F of g of x would be f of, so it's x squared plus 5 minus 3. I think I screwed that up in a previous problem, but that's okay. So this would be x squared plus 2, right? So if I want to know what f of g of negative 1 is, I can, now that I have f of g of x, if I were to say like this is, let's say this is h of x, then I could say, okay, what's h of negative 1, basically, right? Because this is already the composite function, so I'm looking for negative 1 quantity squared plus 2. You can also just look at, okay, what's g of negative 1? G of negative 1 quantity squared plus 5. This is 4, right? And then you take the 4, so what it's really asking then is f of 4, which is 4 minus 3, which is 1. This is also 1. Wait, that's 3. Hold on, do we screw something up again? X plus 3, 4. Oh, sorry, this is 6. I'm sorry, that's 6. So this is 6 minus 3, which is 3. This is 3. So it's two ways of doing the same thing. So if we have g of f of negative 1, I don't remember what this was on the previous slide. So we can take negative 1 and plug it in for f. So we have f of negative 1, which is negative 1 minus 3, which is negative 4. So then we want to take this 4, and it's g of negative 4. And we take the negative 4 quantity squared plus 5 is 16 plus 5 is 21. So you can kind of do it like systematically like that, or if you already have found f of g of x and g of f of x, you just plug in the value for x. So it's evaluating, it's no different than when we evaluate a normal function. All right, here's a slightly more difficult problem, okay? And notice right away that there's a domain restriction for g of x. And the domain restriction here is that the domain is everything from 0 to infinity, right? It has to be positive. Remember what we do? We take the radicand and we set it greater than or equal to 0. Okay? This one's already, the radicand is just x. So we got to keep that in mind. Now, what is hog and go, right? This is actually just h of g of x. This is asking for h of g of x. And this is asking for g of h of x. So h of g of x is going to be h of g of x, which was the square root of x, really, right? So it's just the square root of x plus 10. Now, the domain of this is going to be, we have to consider two things, and this isn't that important for this problem, but will be for the next one. That this is our actual new function, right? Our actual h of g of x is this. So we know that x has to be greater than or equal to 0. And we also know our original function is that x had to be greater than or equal to 0. So both of those things considered, the domain is just going to be the same thing we said before, because it's the same domain for both of these functions. Okay, now what about g of h of x? So g of h of x is, we're going to take h of x, which is x plus 10, right? And we're going to plug it in for x and g of x. So this is going to be x plus 10. So now we have to think, okay, x has to be greater than, x plus 10 has to be greater than or equal to 0. So x has to be greater than or equal to negative 10. So this is going to control, like if h of x had a different domain restriction, then we'd have to consider that in addition to our new domain restriction. And make sure that both things are true when we state what our final domain is, which will make more sense again in the next problem. But for this one, because x, this is just simply the domain would be negative, sorry, that's really ugly, negative 10 to infinity, and that's the domain. Okay, so that is composition of functions. We'll do one more example. So here we have two functions that have problems with the domain, and let's just go out and state what these two domain restrictions are. X cannot equal negative 2, right? And x cannot equal 0. So it can't be either of those two things. So what is this? What's the implications here? What is f of g of x? Because that's what fog is, right? Well, I'm going to take f of x, which is 3 divided by x plus 2, but right here I'm going to plug in 2 divided by x. So we're going to say it's 3 divided by 2 divided by x plus 2, which this makes this pretty gross, right? Because we have an issue where we have a complex fraction. So we're going to need to do the Missy-Elliott method in a second. But notice how we, in the process of doing this, we have this 2 divided by x in the denominator. That if you had a problem, if x was 0 here, we'd have 3 divided by undefined plus 2. That's not a thing, right? So we got to remember that part of our domain restriction, the one we inherit from our internal function here, g of x, is going to play into the domain of the final answer, even if whatever we have for f g of x, we can plug in 0, but we still have to account because we couldn't do it to start with, right? So how do we then fix all this? Well, we need a common denominator of x in the denominator. So we'll say this, don't multiply that 2 by x over x. That'll give us 3 divided by 2x plus 2x over x, 2 divided by x plus 2x over x, which is equal to 3 divided by 2 plus 2x divided by x. Now we do the Missy-Elliott method of complex fractions, which is to put your thing down, flip it, and reverse it. So this is equal to 3 times x divided by 2 plus 2x. So it's going to be 3x divided by 2 plus 2x. Now, in this denominator, right, what would x need to be? X would need to be -1. So we have, in order to make it 0, I mean, right? So that's the domain restriction. X cannot equal -1. So our domain for f of g of x is not only that x cannot equal -1, but also that x can't equal 0. So how do we say that? Well, again, ask your teacher for this, but the domain could be all values of x such that x does not equal, or as long as x isn't -1 or 0. Or in interval notation, -infinity to -1 union -1 to 0, not including 0, union 0 to infinity. All right, now how do we do the same thing for g of f of x? So g of f of x. So we're going to take our 3 divided by x plus 2 and put it in the denominator. So what will that be? 2 divided by 3 divided by x plus 2. Okay, look, again, if I had x was -2, it'd be 2 divided by 2, 3 divided by 0 is undefined. 2 divided by undefined is still doesn't make sense. So we're going to have to remember to put that -2 as, like, x cannot equal -2 as part of our domain for our composite function g of f of x. But we do the Missy-Elliott method here, and we say 2 times x plus 2 divided by 3, which is 2x plus 4 divided by 3, which is actually a line, right? It's 2/3 x plus 4/3. So it's just it's a line with a slope of positive 2/3 and y-intercept of 4/3. But if you were to graph this, if you were to just say this is h of x and graph it, you wouldn't see anything funny going on at all. But if you literally graph this, which we just said is an equivalent equation, right? Then you will have this problem. You will have at -2, there will be something in the graph that you can't have. It'll just be something, and you'll have to go and look. But the domain of this then is the set of all x such that x cannot equal -2. Or again, that the domain is -infinity to -2 union -2 to infinity. So just remember that this internal function here, in this case f of x, and in this case g of x, that is going to have to contribute to the domain, because in the process of finding these composite functions, we can't have an undefined thing and then be like, oh, let's just ignore that was a possibility. That doesn't work. Anyway, that is composite functions. We'll have one video where we talk about a very important application of composite functions, and that application is called a difference quotient. But really all it is plugging numbers in for functions and then doing some division, and it's not a big deal. That video will be coming up next, so keep your eyes peeled, and thank you very much. Hope this was informative.